have to share my screen here. So I guess you guys can see my screen, and so where's my slides here?
Yeah, we can see the screen.
Yes. Let me. Yeah, the problem with this bar here is very annoying. So we're talking about GANs, and I guess I will review a little bit, and then we'll finish GANs today, and then I probably will talk about Boltzmann's methods afterward. So remember, what we have for GANs is a model trying to generate data. So it's composed of a discriminator and a generator, kind of summarized in this slide here. So generator is trying to generate data that hopefully is indistinguishable with some genuine data, and then the discriminator trying to classify whether the data is genuine or not. And then so of course we'll train both this discriminator and the generator at the same time. And then last time we say that we can find the optimum discriminator. So just going through some very simple algebra here. More precisely, we have, let's say, D star is our optimum. Then we change D star with some tiny, with answer arbitrary function. So we change D star, add it with some arbitrary function, and but this function is scaled by this lambda is supposed to be small, and we are thinking okay, for any arbitrary delta, the derivative here should be equal to 0. And then we can just derive that, and then ultimately we will get D star is equal to this. And then we also mention some refinement, or we could mention a couple. Say in the original setup, basically the discriminator cost, we can write it something like this. Something like if the data is if the data is the data is the genuine, then we'll be say for sure. Of course, during training we know the data is genuine. We'll say for sure that this is the discriminator should output 1. So otherwise, if the training data is from a generator, then the discriminator just for sure say that it's a 0. So we can make it less kind of rigid here, not saying that less extreme, always for the training data will be the training data will assume is 1, or whenever we're seeing this data generated from the generator is assumed to be 0, we can go for example like this one here. We can say for the generator, for the true data, we'll just say okay, we'll think that with 1 minus alpha confidence. So more precisely, actually last time I didn't really write it down very precisely. What I mean precisely is something like that. So if I have D star here, so actually I'm doing the same derivation as earlier, trying to find the optimum D star here. So let's say D star is the optimum one, and let's say we also have we have what we just described here, that if we see some true data, we'll say with 1 minus alpha confidence that is true. So what is that mean precisely? It would be like that. It would be I have a causal entropy loss. This is a causal entropy loss that whenever I see the, let's see, yeah, I have the D star here, D star, or you can think of I have this whole term together, but let me just call D here, just call T here. So I have D that because I know it's a true data, so for dx here, I will have some value here, right? So if this, let's say this is x is true data, I have for true data, sorry, what should I say that? So for the class that classified to be true data is dx. For the score classified as not true data will be 1 minus dx. And this is what we get like when we getting out of the discriminator network. And ideally, the ground truth here, we are saying that like, okay, you want to have basically if it's the true data, then it's 1 minus alpha there. And if it's for the class, okay, this is I think I say it rather confusing. So think of like this is like two different classes here, right? We have class is genuine, that's true. I have a class that's fake. So when I go through the discriminator, it's like we spit out two scores. Right? You think of like, of course, you can summarize the one score, but it's really like two scores with a probability that essentially you see this x here, you decide, okay, what's the probability that d after all is like kind of a belief or like probability, right? What's the belief that like x is genuine will be like given by d, right? So this is like, so I want to tune dx to be what I desire. So what I'm saying, like if x is genuine, x is true, then I would want something like that. I want to have these two distributions to be close to each other, right? Something like so originally, like if I don't, I go for the original GANs, basically alpha will be just 0 here. So here you see that like I don't set the confidence like to all the way. When I see x is true, I will not say all the way like it's definitely 1, but instead I will say it's just 1 minus alpha. Then as usual, like if I want to have this guy approach this guy, I use the cross entropy loss. Then the cross entropy of these two, now it appears like two distribution will be just like 1 minus alpha log dx plus alpha log 1 minus dx, right? And this is exactly this term here. That happens when your x is drawing from the actual sample here, actual data here. And if you're drawing from the model that is a general data, then it will be exactly flipped, right? So I want now if this is like this x here, now if this x this time is fake, then I want dx should be close to beta, and 1 minus dx close to 1 minus beta, let's say, and beta is like some value less than 0.5. So typically some small values. Both alpha and beta are supposed to be some small values here. And so then like you have this here. Then we can go through the exactly same thing. Eventually you can derive the d star will be equal to this that we just showed last time, but we didn't actually go through that carefully. But we say that like this is actually no good, because if d star is given by that, I mean like it's good for this guy, this side. So that's why people say that it's good to do this one-sided label smoothing. So we just only smooth the part that when the incoming data, the data x here is the genuine, is the actual training data. But whenever it's generated, then we are not going to have like this beta is not equal. It's not going to set to be non-zero. So any question at the back? Like I hear some. So it's a kind of review, so therefore I go a little bit fast here. But we also mentioned that this is, as I said, like beta is non-zero is not good, because if beta is non-zero, what you're seeing here is like for the x that is, it's not happen like often like in the data. So that means that if p data x is small, is close to 0, then what happens is like if this beta is non-zero, then you will have like d star x is going to be big, right? So what I mean is like even my data it does not appear in the actual data here, or like it's not likely to happen in the actual data here. I will classify it as genuine because of this term here, because beta is non-zero in this case. So therefore, like typically it's just one-sided labeling, so we don't have this beta, but we will use this alpha is non-zero here. So, and we also mentioned a batch norm that we can have this virtual batch. The batch norm is good, but it can have artifacts. A simple fix will be we'll have a fixed norm that we call a reference norm, that each time we'll just compute the statistics using both the current batch and the reference batch together to compute the means and variance and normalize to that one. Then okay, we ended here, so we gave a 10 12-minute introduction here. So we ended here. So what we mean, okay, here this line I want to say is that like we have G and D. So but in practice actually we oftentimes it's more important to have a good D than a good G, or I shouldn't say that, but it's really important to have your D to be good. Like your never make your D, I mean try to limit your D so that you think it's too smart. So for example, like you see like you always cannot kind of like train a generator such that it can fool the discriminator. So you're thinking, okay, maybe I would just like lower the difficulty here. I will make the D a little bit dumb so that occasionally it will just make mistake and classify something that is not genuine into like something. Like something fake and assume it is genuine. And it's not good to do that. Like because if your D is dumb, then definitely what you generate will be garbage. And sometimes it's not intentional. Like you're not really trying to make a D to be dumb. But if you look at actually something interesting is that like you have this game theoretic problem here. So we of course we have the cost for the generator and we have the cost of discriminator, both of them trying to minimize their own cost. But also we can look at it as a minimax game, because like essentially the generator cost is actually just the minus the cost of the discriminator. Even though you can omit some term for the generator there, but essentially they just like the negative of one another. So then I can write the problem like this way, really a minimax problem, right? Or like a max min problem here. But these two problems are not exactly the same. I mean, it doesn't always get you the same solution here. Of course, if your objective function is convex, somehow it will give you the same solution. Or it's actually not exactly convex, but how to I think it's like something like it's like what was that called? So but anyway, so in general, like it won't be the most important thing I want to point out here is like in general it won't be equal for these two optimization problem. Okay, by the way, like to even get further, like just pause you guys a little bit. Which one makes more sense? Do you want this one or like this one?
The one by the right.
Yes.
Why discriminator is trying to minimize, the generator is trying to maximize what the discriminator has. So I'm thinking the one by the right. I'm not sure.
Yes, yes. Actually, the solution also here, but it's kind of hidden here. Yes, you are right. Definitely, you're right. So you would like to have the discriminator in the loop or like in the inside. So when you what what is things in the inside has more oh, I don't know how to say it. So have more control with your I'm thinking like if I can just create example to let's see. Let's see if I can scratch something. If I have, let's say this is the discriminator, this is the generator. I think of like a minimax problem here. Let me just arbitrary. So let's say if I want to let's see, I need to one of them I need to minimize. Yeah, actually, even that we can kind of see that like for if I have this is the actual score here. If I'm doing the minimization first, oh actually this one actually in both cases will yeah oh okay, it's still okay. So if I'm doing minimization first, like I will actually ended up here, right? Is that here? That's it. Minimization and then maximization. So I ended up here, but if I'm doing maximization first, I'll end up here. So if I'm having the generator trying to maximize first, then generator will pick this. Wait, I guess I swapped the two here. Generator picks this, minimizer will pick this. If I minimize first, I'll pick this one. Oh, actually, both of cases I will pick the same one. Maybe I should swap something here. Let's see. How about this? So if I have, I'm going to do maximization first. I will maximize, then minimize. I ended up here. Let's see if I no mass. Oh, okay. I really should be. I'm kind of even confusing myself. So so if like G is allowed to maximize first, then G will pick this row and then minimize. I will get this one, right? But if D is allowed to minimize first, I will basically pick this column, and G trying to maximize, I'll get into this one. Did I do something wrong here? Let's see. Oh, I guess I am really not careful here. If I minimize over d here, I should get like 0 over this. Okay, I can pick minimize over this one. I have 0 and also 2, and then maximize. G should get 2 here. Yes, this is like d minimize first, and then if like G maximize first, I will have taking this is like 3 and 2. Okay, okay. I do not, I cannot get give you a good example here, but but inner loop is supposed to give a bigger control of the game here. So if you want to make something smarter, like for the discriminator, you should put D in the inner loop. Okay, I don't want to spend more time on this one. So, but I think like you can create some example yourself and play with that. Like I forgot, like I did that like in the past, so I can't forget that. But if you accept that, what's going on is actually this is also an illustration that if we consider like these two different implementation, because like one way to implement that is like when you first do the minimization and then the maximization, it's like you have like the discriminator, something like you're training your model, and you have the discriminator in the inner loop trying to have some discriminator update. Let's say you have the update here, and then there's some loop here, then maybe some loop here for something the update, and then outside you have like G update here, and then maybe you have more loops here. This will be like for the right hand side case, and for the left hand side will be exact opposite. Basically we'll have like the G update is in the inner loop, and then the update in the outer loop. And this has a actual difference like when you actually implement that, like for GANs. For example, like this illustrates that, let's say you have a target distribution is like this. This is like in the feature space you can think of like this. You have the actual target. You will this is not an image. This is like the feature space. Like you think of like I generate data in some high dimensional space. Sometimes the data will be here, sometimes it will be here, so on. So this is just the distribution of the data. And if I put G in the inner loop and try to train it, or like you can think of like if we just iteratively do G and D updates like iteratively, we'll have like result like this. So we have the first step is like that, like this is 5,000 steps about to 25,000 steps. So it eventually converge, but it only converge to one of the mode of the target distribution. So this problem is known as the mode collapse. So something like you can think of is like you're trying to generate, for example, images. Like for example, like I have some image of like some I want to generate some image of some fruit, and then like it always give you oranges. So even though you expect it also give you banana, apple, and so on, but it only capture one of the mode basically. So only give you one of the mode there. So one way to kind of mitigate this problem is like using this kind of like avoid this mode collapse. So a very simple idea would be simply whenever you generate sample, you check the distance, like in terms of the feature space of your generated sample from the already existing samples. So if it's pretty close to the existing samples, you just discard that the currently generated sample, and you regenerate it again. And of course, a more kind of um, direct way will be, as we said, like we're trying to make the D step a bit smarter. That is exactly make them the inner loop. Actually, this is exactly what I'm drawing here. That we're going to make D in the inner loops here. So, for example, like we will each time we update D for k times, uh, for every k discriminator update, then we update once the generator. So this is an illustration here. They call this unroll GANs. It's precisely just you do k step like discriminator update before you do one step of generator update. And for this particular example, you see like it can converge to the actual distribution much better.
I have a question.
Yes.
So, Dr. Chang, for numeric data,
Yes.
data that has figures and numbers.
Yes.
If the training data has samples like 10, or even numbers like 20, 40, 60, 80, and then you want the generator to generate numbers in between this, numbers in between 20 and 40, more like 22, 23, in between. Is it possible? Because I know the generator tends to indate the training data. So can the generator interpolate, like give big numbers in between the training data?
Yes, yes. The actually, if you maybe go back at the beginning, oh, I'm not sure. Like actually, some other slides at the end, but actually, even look at this. Like um, you always have a random input at the beginning. So it's okay. It's not or like maybe more back to in the beginning. That's right. So for the generator, it always accepts some random number generator at the beginning. So this when you generate, you of course this is a lateral model that will go for example, it can be a fully connected lateral, say with some weight multiplied by this random number generator, and then I have some activation and then another weight and so on, right? So I mean the output here will be continuous, so you don't need to worry about that. The point is I just when you generate this one sample, this discriminator have the task to make sure that what you generated will be similar or like tough, it is indistinguishable from your data sample. But if you say your data sample is always give you like 1, 2, or like something like some fixed number, then eventually, of course, it will realize that the only label or like any only data you want is like will be like that. But I think like this is not a very reasonable use case for like GANs. So we expect like data sets like much more complex that we don't expect we can see the structure very easily. So did I answer your question? Kind of.
Oh yeah,
Maybe.
kind of, because I did
Yeah.
something very similar,
Yeah.
and it was giving me just some continuous values, but it was giving me continuous values that when you approximate them, they were equal to the training data.
Yes. Yes. The training data. Yes. The training data can be continuous, or I mean the yeah, it will be continuous because I think most of the time we assume continuous, even if in image, of course, we can approximate to be discrete, but because only have 255 levels, but practical purposes, we can think of as continuous. Um, yeah, I think most of the case is the generated data is continuous. So, and now then, okay, maybe just mention one of these model also because it appears in the homework. It's a kind of like modification called least square scans. It just like modify the loss and the generator and the discriminator loss so that numerically it's more stable. So again, it's pretty intuitive because this is like if your data is like generated, then you hope. Wait a sec. uh, discriminator. Oh, okay, yeah, this is this is okay because this is generator loss here. So then I want to make sure that like I will be able to fool the generator, right? So if my this is the data generated by the generator, then I hope the discriminator is thinking that this is genuine. So therefore, I want this DGC to be 1. So in terms of the discriminator perspective, then if the data is actually true data, I want that to be 1. If it's like fake data, I want it to be 0. So just a slight modification like this. And then see another application here, more realistic, like for so-called DC GAN. So it's trying to combine with like convolutional neural networks. So it's not really something very special here. So we again I guess like the discriminator is nothing special because we study classifier for many spent quite a lot of time on that already. And in terms of the generator, it's also like I think at this time shouldn't be too surprising. You start with like again like some random vector here, then the generator is like doing this upsampling. That you see in some of the earlier classes is like the transpose of your convolution, and then like you can also have typically you can just do transpose of convolution, then you can do upsampling like this. So you start with a vector. You first like kind of can have this dimension is a little bit weird, but let's assume that like you cannot of course like resample that like actually I'm not exactly sure how this dimension goes here. I guess you need to get into the paper, but it shouldn't be like something very kind of surprising. So 100Z. So okay, anyway, maybe I shouldn't spend too much time here. But once you have this generator, then like again do the same thing like with train the discriminator and the generator at the same time. And this is the result training this like Elson data set, like it's a Batum data set that result looks pretty good. Like I guess like by this time like you see this before like in some of you guys others presentation, so you won't be very kind of like feel impressed anymore. And but pretty interesting. It's like if you think of this C here, this input vector here is like it does have some embedding kind of like features like in natural language processing. It kind of like extract some of the semantic information of your final generated image. So for example, like this is like pretty interesting experiment. Say if you have images, like this is images generated by different like z vectors here. So let's say like these are images that I'm just going to take average of this all the images that I can find that is a smiling woman and that have like different z vector. I can like average that. I have an average image of like a smiling woman, and then I also have like this is a neutral woman faces. Then I can find some like neutral man faces. Then I can just manipulate this z vector like just as in word to word. Like you have when you have smiling woman minus neutral woman plus neutral man, you can't expect like smiling man, right? So you can generate like images of smiling man here. And you have this other example like man with glasses, like this is man without glasses. Then you have at woman with glasses without glasses. Then you have like woman with glasses. And but GANs are not perfect. Like I think like many people is trying to tackle this kind of problem. I wasn't keeping track very closely with the current progress. So, but this definitely is one of this problem. It's like um, you can generate images, and they actually the model, for example, is trying to generate this. I think it's like animals here. So they you can see the models like kind of figure out like when you have eyes here, you expect the nose is here, but the model is not very good in terms of countings. For example, you can see um, animals that it looks like have more than two eyes and then like more than like four legs and so on, or less or more. So uh, and um, and this is another interesting work that basically doing an opposite of like uh, captioning. So we just input a sentence here and then trying to generate an image that that is like related to that sentence or like so for example that this image here first you will do some word embedding, right? Basically this image here you become a word embedding vector, then um, you can go through some layers here uh, and combine. So you once you have this generator, I guess you need to get into detail. I'm not sure how. There's lots of should be lots of detail, but in this particular work, like they actually did a multi-level generator. So they have a lower resolution level that generate this image here, and then they have the some view image. Then you have discriminator that for like both kind of like lower level or like lower resolution discriminator that are trying to discriminate whether something is this image is like genuine. At the same time, we compare with the word embedding of the input sentence. Also, they want to make sure that there's an additional loss there, whether like your image actually is as the sentence described. Then you can go. I mean, take the current image and also like the sentence embedding, like just generate a higher resolution like image, and then like continue to uh, have a. Of course, you can do layers, but I guess like this one only two layer, and then you have a high resolution image, then can go for a discriminator again and so on. So you have this combined loss for the discriminator, uh, and you can see like there's two stages that have some real gain here. This is the first stage is it's like this, and then the second stage is very realistic actually. Um, of course, this is pretty old, kind of like 3 4 years old work already. I remember the stack GANs, purse, and so on. So if you guys are interested, you can look into that. Um, and there's another like work that uh, is quite interesting. Like if you are an artist, that's basically you can use. This is like also like an illustration like how you may utilize GAN. Like it's trying to like just sketch a stroke here, just draw one line here. Then like you will figure out that like okay, I maybe I'm trying to uh, make a green field here, and then you draw another curve here. You think you're drawing a mountain. Basically, you draw a couple lines here. It will create an image like this. Um, so this is old, but still like people of course like still have lots of interest in GANs. I probably will still have this interest like for many more years to come. And there's some links here, probably like a little bit dated, but if you're interested, you still can look into that. And and so there's some variation, like for example this WGAN, like actually there are many variations trying to adjust the loss functions to make it more stable. Um, as I said, this is a very kind of active research area, so um, yeah, but anyway, I guess I will just stop here for GANs. I won't uh, talk more on GANs for the So any questions? So I have half an hour left. That I will just start with something a kind of a new area here. So exactly not very new. Actually, we go back a little back history. So I like to talk a little bit about Boltzmann machine. Uh, so it was kind of like invented by Jeffrey Hinton back in 80s. So it's actually pretty intuitive models. It's strongly kind of influenced by physics. So it's, you basically have a graph model like this. You have a kind of connected graph models. So each of these nodes here can be variables. So it can have tick values. Typically, like we consider a Boltzmann machine model with like output values is only 0 and 1. So unlike some of these other models we study here, is actually a binary models here. Uh, and like other physics models like you study maybe in statistical mechanics, the configuration, like whether like for example whether I have a configuration this 0 0 0 1 0 1 0, or like maybe I change to 0 something like that, the configuration depends on the likelihood of like the probability of this occurrence, which depends on the energy. Basically, it's governed by a Boltzmann distribution. So precisely like that. So you will have a exponentially uh, smaller probability as the energy increases. So in the sense you want to go into the lowest energy state, um, and the energy function is simply linear like this. So it's like just a mixing um, of this each of this. So basically, this x here is a in this case I have 7 node here, so x will be like a 7 by 1 factor here. So I have like x0, x1 up to let's say x6 here, and then like this one like w will define the like node to node, that kind of like correlation, second order like correlation of that energy coupling. And then C here is just a bias, then like whether it's like a node is like you can think of is whether it's like in a positive or negative state, then you have different energy basically. um, and typically like in models like this, you how we are going to use it is like some of the nodes here will consider as hidden variables, and then some other nodes will be like input, let's say, and then some other nodes can be output. So for example, like if I have a pretty big lateral here, so I'm doing some kind of classification. I have inputs like putting in some of the nodes here, then I will just let this like Boltzmann machine run. That I want to, what I mean one is like I want to see if it will kind of like slowly converge to the low energy state. Then after it kind of like settle into low energy state, I can read back the state at the output. Then I can use this to determine whether was, for example, if a classification, I can just read the labels here basically, whether the input is like a cat or not a cat, let's say. Um, so Boltzmann machine itself is a very rather powerful model. Uh, yes.
So what's the size of the W? 1 by 1, right?
No, this is a matrix here. So okay, let me.
You talked about the X is 7 by 1, and so the X transform should be the 1 by 7.
Yes. So therefore,
So,
this is
so
a 7
when
by
you do
7.
the
Yeah.
calculations, the W should be the 1 by 1. So the matrix.
No, 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 no. So this is 7 by 1. So therefore, W should be 7 by 7. So this is a 1 by 7.
Yeah.
Yes. So yes. And so C is also like, so in this case would be like also 7 by 1, something like that. If you have like 7 nodes here, so if you have n nodes here, w will be n by n, and then like c will be n by 1, something like that. Yes. And okay, yes, as I mentioned here, like Boltzmann machine is powerful, but as you can see, actually when you use it, like it's pretty tricky. So we will need to discuss it more, because when we kind of fix some of the states here, what we want is like, let's say we want to read out the output here. The output is the configuration that is the low energy state. Basically, we want to like look back at the low energy state, and how do we get the low energy state? That we typically can be done using simulation. So therefore, you can see like this is actually itself like it's not really like any of these feed-forward lectures we kind of like discuss in the entire class. This is a totally new piece here. So even you doing the inference itself is not just, I mean, like have some feed-forward lecture, like just you have like a couple multiply several layers and then like do several like soft math or like I mean value and so on, then done. Here like you need to like have lots of like computation here. So and this is just doing inference, and you train the model, you need to actually learn this WMC, right? So therefore actually the whole model itself is pretty challenging to use. And in the mid 80s, Paul Smolansky, like he proposed like a kind of like restricted version, like along with the restricted Boltzmann machine. Well, actually, there's an original name like Harmonium. I guess no one actually used this name. And actually in mid 2000, around mid 2000, like Hinton like kind of like derived some fast learning algorithm, the restricted Boltzmann machine. And actually it was used to help to train deep neural network at that time. This is like in kind of directly led to the renaissance of like the deep neural network, actually of neural networks really. So actually, you see historically, this is actually very important. Now, what's the restricted Boltzmann machine? This is a just like Boltzmann machine, but it basically just instead of an arbitrary graph, it changed to a bipartite graph. So basically, you have like the hidden variables on one side, and then have the visible have this x here, the basic variables in the other side. And it's a bipartite graph. Therefore, like within h here, like there's no connection between those. For example, I cannot have nodes here connecting to this node, or like nodes connecting to this node. Similarly, for the variables here, the visible variables here, the x here, I cannot have like this x connect to this x, for example. So because of this limitation, this restriction, we can rewrite the energy function like this, right? So basically the coupling will be only from h to x, so I can have a w that's only couple h and x, and also like I will have like this local energy term for x and h as well, something like that. So therefore the joint distribution will be just like this. So if I given some x and h, then the distribution should be just given by like this one. And by the way, this is z here is just a normalization factor. In physics, it's just known as the partition function. So it's like in this case here, actually c is just equal the summation of all x and h exponential minus e x h here. And this is the basically like to do the sampling here. So what I mean is like the sampling is like if I given that some x here, as we mentioned here, like how we use it. Let's say I'm going to classify whether something is a cat or not. maybe his is the input I put into the X here, that's the input I plug into that. Then I let the model run. Then eventually I read out this guy to decide, okay, whether it's a cat or not. So then I need to let the model once, right, basically simulate, let it slowly converge to the minimum energy state. So to able to run that simulation, I need to know the conditional probability of this guy, like h given x and x given h, because how we're going to do the sampling is using this known as the skip sampling here. Maybe you heard of that in physics. So it's a very simple idea. Basically, for example, if I need to sample, for example, I fix this x here, and I want to sample the configuration. So I want to just reach the low energy state somehow. So what I can do is, given this x, I try to sample each of this h here, right? So I can, so for example, for this h1 here, I can compute the probability of ph1 given x, right? Or then maybe ph1 given 1 equal given x, something like that. So based on this probability, I will determine like whether this one should be 1 or 0. And then after this one is sampled, then I try to sample this next guy here, and sample this next guy here, this guy here, this guy here, and so on. And then once the entire H layer is sampled, then I can go back and try to sample this guy. Or maybe like if if not all of these are fixed, maybe I just have like maybe some of them are fixed. But actually initially I still like need to put in some values here. Initially I don't know what is that, but maybe I need to put in some values here. And based on these values, I will try to sample each of these again, as I said. So once I sample each of these here, now because this is kind of fixed now, then I can try to sample these two again. I mean, I can sample this and sample this. And now I have new values for these two guys, then I can resample this guy again on the upper layers again. So I can do it back and forth. In either case, I need to know this pH given x, right? Or like this pH j given x. And first thing first, like because this is a bipartite graph, and you see that h within the h layer it does not connect to itself, therefore it's like conditional independence, right? So pH as a vector given x is just equal to phj given x. So the product of them. So we can look at each of them individually, just as what we did in this sampling here. And this one, if you try to compute, that will be just equal to this guy here. Actually, I can go to the next slide here. So phi equal to 1 given x will be just equal to, let's see if I remember that, what's the p this slide is a little bit bad, it's too far away. Let me pause, write something here. So the original expression is something like that, p h x is equal to this exponential okay, because of time, I guess I won't go into detail like this. But you basically what we have here is if we write down the expression here, some of the terms will get like cancelled, so we only have these terms left behind here, and also like the denominator here is like a basic normalization factor. You remember the c there is a sum here, so we will sum over like different value of h, basically 0 or 1. There's that basically just two terms here, so therefore equal to this one is equal to this guy here. So then therefore we have this pH using this, basically we are able to sample it. That's the main point here. Is we have like h given x is equal to this guy. X given h is basically the same expression, just with this flip a little bit. And as I said, like when I have data generation, I can just use skip sampling like this. I sample for the x layer. I given the x, let's say either x or h is fixed. Then I can sample the, if x is fixed first, I can sample the h layer. Then I can sample the x layer and then h layer and back and forth like that. So that one we have this is like px given h or ph given x is compute. We also want to look at the marginal probability, because that's the probability that like if I have some data is appearing that. So for example, like if I have some data x here that appear that I want this to be big, right? If I just want to make sure that if I have a model, so basically what I mean is I want to maximize intuitively, we kind of want to do something like that, right? If we have a data like that, it's not exactly doing like that, like, but you will see. So if I have like xt is a data point here, so I want to make this thing big, right, with respect to this w, c, and b. Basically, this is the variables here. Right. If x is actual data, I will want this one to be big, right? So therefore, I need to know the expression of this marginal probability with respect to like w, c, and b. So and then we just have like the pxh is equal to okay, we have pxh is equal to this guy here, or something like this, and px is just marginalized that way. It's just pxh sum over all h, right? Sum over all h. So therefore, I have this is actually pxh here, sum over all h here, and all the possible h here, I can write it as a list of sum instead of just a single sum in a list of sum here. And this terms does not depend on h, so therefore I pull it out. I have this one here, and then this guy, like sum of this exponential, I can rewrite as a this product of sum, basically. So it's a product of each of these term here, and then h is equal to 0 and 1, so therefore like each of these sum here become just like this. And then when we plot that, this guy, I can rewrite this as like exponential log of them, then therefore it becomes like exponential cx like log this guy, something like that. So therefore, like we have a rather clean expression for the final marginal probability here. And by the way, this expression have a name for that. It's called a soft plus function. Honestly, I didn't think too much why it's called soft plus, but it's just called soft plus. Now, this soft plus function is actually just the wait a sec. Yeah, just the integral of the sigmoid function here, really, actually. If you take derivative, okay, wait a sec. Yeah, if you take derivative of this soft plus function, you should get the sigmoid function here. And also, like this entire terms here, typically people call it the free energy, like use expression like minus fx here. So in terms of training, as we mentioned earlier, if I know the p here, so I know the p expression here. Of course, this p is parameterized by this w and c and b and so on. So now, if let's say if I have some data points here, I have x1 up to xt, let's say, right? So this is a data point I see. So let's try to maximize my model using cost entropy loss. So well, what you can think of is like the genuine distribution should have a distribution like each of these guys have like 1 over t probability, right? Now the distribution I have from my model will be like px1 up to pxt here, right? So now if I compute the cost entropy loss is what? It's like we have something like, if you remember, it should be like the cost entropy loss is qx I log pxi, something like that, right? And sum over all the I here. I think that maybe there should be a minus sign here somewhere. So, and this qxi here is just 1 over t. All this is just 1 over t. So therefore, I have this expression here. So 1 over t, sum over minus log px t here. Okay, here I use t, but here I use I, but the same thing here. Then we know the p is just equal to this way. Earlier we said p is just equal to exponential what's that? Minus f x over z, something like that. Okay, so this is px here. So if we log that, we have minus fx here, and then we have minus no c here. Yeah. Wait, actually. So anyway, and then if I just look at one of these terms here, so let's say I trying to minimize the anti-cost entropy loss, but if I only focus in one term here, one of the t here, so if I look at the gradient, see how it changed with respect to the parameter. So take the derivative of this one will be just equal to taking derivative like fx, and I have I have this is basically c is equal to exponential minus fx sum over x here. So and this is a little bit where am I? A little bit getting lost myself. So I think I should really just write one step at a time. So I have f px as we said here. Log px is like f. Oops. I guess I'm trying to watch. It's even worse. So maybe I should just slow down. Minus log px is equal to f x. Maybe I will just skip the t. This is too much t here. Minus fx is equal to fx. So px is equal to exponential minus fx over c is equal to exponential minus fx sum over x. So then I take the log there. So it's a minus log sum over exponential minus fx. Okay, something like that. Yes, and I I take the derivative of this guy is just this guy, like derivative fx is just this term here. Take the derivative of this term here, have 1 minus sum over x experimental, so minus fx. Or this is actually just c here, so it's like also this is actually just c here, so there's this c here, and then take derivative of this guy, have like exponential minus fx here, and then take derivative again, like I have partial f partial theta here. It worried me a little bit. I think there's a minus sign, a plus sign here that should comes up, but so assume that like the expression is right here. Okay, then you see it's like I have this term here. This guy is actually, turns out it's just px, right? So it's again like something pretty interesting. I think we saw this something similar before when we discussed like word to web. We also have something like the gradient is kind of like you have one term is just partial derivative of something, and then afterward it's like the expectation of some other thing here. And this is like, okay, for the positive one, the argument inside is actually the training data, but for the negative phase, the argument inside is like all the other elements here, all the other x here. So I mean, like this one, like it's a pretty clean expression, but if you think of that, like what we've written down this one, actually the actual computation here is sum over all the x here, right? So it can be computation very expensive. So in practice, like because like this is actually trying to do a expectation of this guy, I just take an average of this guy. So we can really do Monte Carlo to approximate that. So for example, like we can sample several of this x here, then we compute this partial fx partial theta, and then take the average. And we can even go more extreme. A more extreme case would be like we not even like sample couples of this x here. We just sample one. So sample one will take a represent as a representative. So we will just sample one x here, and then use that like to approximate this expectation partial f partial x theta, and approximate as just partial f x tilde partial theta, something like that. And this is like very popular or like very famous algorithm like in restricted Boltzmann machine, and it's so-called the CTK contrastive divergence like K training, that you sample. We start with some training data here xt. Then we sample this guy like from x. We can sample some h here, right? And from h we can sample back x, and we can do it repetitively. In practice, we just do it k times, and then afterward, this x tilde will be the sample we are going to use. So as I said, like instead of sample many of this x here, we just sample one x. We take one x tilde and use that as a representative of this the second expectation there. So therefore, like we will have the gradient will be replaced by this. This is the xt again. Is the it's the training data. That data you from the training data there, training data sample, and x tilde will be like sample using this CDK. And actually this is called CDK, but surprisingly CD1 work pretty well. Like often like people just say sample once. So you have x here, you sample h, and then from h you sample x1 again, and the first x1 you will use that to approximate x tilde right away. So with that, then like actually we can compute precisely what's partial f partial each of these parameters here, we have theta here are all the parameters, right? But actually the parameters in the model is basically c, w, and b, right? So we can take the individual derivative here. So for example, like taking partial derivative with respect to c, it's just called x here, right? If I take partial derivative with respect to b here, I will have the derivative of this guy. The derivative of surplus is just sigmoid, and then take derivative of b here. This guy just nothing here. So if I take derivative of like wij, I will basically have an xj coming out because there's a wi here. So but anyway, like with some algebra, you can see the update rule can become like this. So you have whenever I have c, or actually I'm already kind of running out of time. So I guess I was kind of behind from what I want to cover, honestly. So I guess that's why I'm rushing a little bit. So but anyway, I guess let's continue first day then. Like, do you guys have any question? Like, let me see if I have anyone say anything. So okay, if not, then I guess we'll just stop here. I will meet with you guys like first day then.